So let's talk about buffers. Buffers usually uses the concept of common ion effect to make it work. First, what is a buffer? So you have here different buffers. When you go to the lab, you will see that they're just solutions. They're in water, and they have different pHs here, pH 4, 6, 9, okay? So what a buffer is it is a solution that prevents the pH from changing. So if you have a beaker, and right now the pH, if you have the buffer, let's say the buffer's at pH 4, and if you add acid to it, H+, the solution will stay at pH 4. That's what a buffer is. And you might be wondering, why is that important? So buffers are used most for biological systems. Let's say proteins. Proteins, of course, have amino acids that have different bases that are positive, that are acidic, basic, or neutral, and there's hydrogen bonding. So if you change the pH of that protein, it will denature and then you lost its function. So that would be bad if you had enzymes, which are proteins, and they don't work. That would be really bad. So what we do is we would put them in a buffer system, and that's what you have in your body as well, okay? In your blood, you have buffers. So if you wanted to make a buffer, what would you put in it? Okay, remember, when you add H+ to it, the pH cannot change. So what would you put in your buffer? This is your buffer, so that the H+ will be taken and not change the pH. Sure, I would put some NaOH, let's say, in there. So NaOH makes Na plus and OH minuses, and the H+ will react with OH minus, and then it turns into water, so it's no more, okay? So you can put NaOH in your buffer, okay? What if you wanted to add some OH minuses? NaOH is not enough to be put in your beaker, right? What else would you put in it to react with the OH minus? Sure, you can put some HCl in there, and the OH will bond with the H and make water. So you didn't change the pH. But the problem here is when you mix these together, let's say you haven't added anything yet, these two will neutralize each other first. You're going to pretty much make salty, Na plus Cl minus is floating around, and water. When you mix these two together, you're going to have salty water. Then when you add the H+ and the OH minus, it's not going to buffer. So whatever you add in there, they must react with whatever acid or base that you add, but they cannot react with each other, okay? So what would you put in it then? Well, first you need an acid, so it'll react with whatever base that you drop in there, right? So that's a given. You need a base to react with whatever H+ that you add in there, right? But they cannot consume each other in a neutralization reaction. So what you would do is you would use a pair, okay? First, let me tell you, because if they're pairs, conjugate acid and base pair, you have the acid, you have the base, but they're paired with each other, so they won't react with each other. Let me give you an example. Okay, so here we're going to put in an acid, CH3COOH. CH3COOH, this is acetic acid. Okay, that will work because even though it's a weak acid, if you add OH minus in your buffer, this OH will steal the H anyway, even though it's a weak acid, right? So adding that will work. So you take some acetic acid, drop it in your buffer. Next, you're going to add its conjugate base. So the definition of a conjugate base is they have to be different by only one H, okay? By one H+. If they're different by two H+, it's not going to work. It needs to be different by one H+. Okay, so the conjugate base of this is CH3COO-. That's the conjugate base. So you might wonder, well, how do I buy that? From the store, the acid is already in a jar. Okay, just pour it in. It's in the liquid. It's aqueous in water. This is going to be in the form of a salt. It's solid. You're going to drop some of this in there. The Na plus will float around. It'll do nothing. So pretty much you have that in there. So you add your sodium acetate salt. What will happen is this. If you add the H plus, okay, this will grab the H plus that you added. Okay, so, but you have to pick a base that is strong enough to extract that. Okay, because if you have like a Cl minus, that doesn't want the H. Like let's say you put HCl and Cl minus, those are conjugate pairs, right? Right? Well, okay, the OH minus will grab will grab the H plus, fine. But when you add H plus to it, is the Cl minus going to grab it? No, because it doesn't want the H plus. So you can't use a strong acid. You have to use a weak acid. That's the key. Even though it's weak, the OH minus will steal it anyway, will steal the H anyway. The reason you want a weak acid is because you want the conjugate base to be strong. Okay, if that's a weak acid, that means it really wants the H, which means this really wants the H. Really wants H pluses. If it really wants the H pluses, then if you add H plus in there, it will grab it. Okay? Because they're pairs, they will not consume each other. Those won't react with each other. They won't neutralize each other. Okay? So you can also have a weak conjugate acid base pair. So you can have a weak acid or you can have a weak base. Weak base. And if that's a weak base, then NH4 plus, which is its conjugate, is going to be a strong conjugate acid. Now you might wonder, well, not as strong as the top 7. It's just a strong acid compared to its conjugate base. Okay? So what you can do now is you can change the concentrations of these pairs. And oh, one more thing is this NH4 plus, you can buy it in a salt form, ammonium chloride. It's a white powder, and the Cl minus won't do anything. You just put that ion in there. Okay? By changing the amount of these conjugate acid-base pairs that you add in your buffer, you can have a buffer at any pH. Let's say you want a pH of 4 and not a 6, then you can just vary the amounts, and I'll show you how to do that. Okay, so first, how do you make them? What acid and base do you pick? Okay, first you have to consider this equation. So this is HA, this is the acid, so this is a plus and the minus. The A stands for any acid. It could be HF, let's say. So plus minus, the A would be the F minus. When this dissociates, you get that. The Ka would be H plus times the A minus over HA. Okay. So, rearranging this a bit. Oh yeah, so what you would do if you put equal amounts of each, let's say it's HF, okay? Let's say you use equal amounts of HF and F minus. If you make those two equal, what they will do is they will cancel each other out. So if if this is the, let me just make another equation. So HF becomes H plus and F minus. Okay, so Ka is equal to H plus times F minus over HF, okay? This is the same as that, I'm just being specific here. If you put in the beaker equal amounts, okay, so you're gonna drop in equal amounts of this and this, the HF here will cancel with this. So your Ka will be equal to H plus, okay? So if you take the log of this, negative log of Ka, and you take the log of both sides, negative log of H plus, you're going to get pKa here is equal to pH. What you've done is the pH of this buffer is going to be equal to the pKa of the solution. Okay, so let me tell you what I mean. So let's say I want to make a buffer. This is the first thing I do. I go to my Appendix D, okay? And then I go shopping. I really want to buffer something at pH 4. So what I do is I look at the power of, this is the easiest way to do it, okay? These are the Ka values, right? So if I do negative log of this number, 6.8e negative 4, I'm going to get the pKa. So go ahead and do that. 6.8e negative 4 log. Negative 3.16, multiply by negative 1, so it's 3.16. So this is the pKa. Let's say I want to make a buffer, and I want that buffer to be pH 3.16 buffer. Okay, and I want to sell it to the whole world. I made this buffer. It buffers solutions at pH 3.16. All I need to do is I need to get some HF, put it in there as part of my buffer, and I need to get some F minus 2, right? Because I need the conjugate pairs. And you might say, well, how much? I need to make equal, right, put equal amounts, because if I put equal amounts, of the acid and the HF, then the pH will be pKa. So going back here, if I put equal amounts of HF and F minus, then I will have my pH to be 3.16. So I would buy from the store some HF. I would also buy from the store some NaF. It is going to be a salt. And mix it in, and I have a buffer at 3.16. So when I add something to that, let's say an acid, it'll stay at 3.16 because the F minus will grab it. Okay, let me make another buffer. Let's say I want to make a buffer around pH 8, right? So what do I put in it? I put some of this, HClO, and I want the conjugate base, ClO minus. And I want to put equal amounts of those two, and my pH of this buffer will be the log of that number. So let's log that number, 3e negative 8, log it, 7.5. So I can sell this, put it in a bottle and say, hey, buy this from me. I have a buffer that's 7.5 pH. So when I add a foreign acid to it, it'll stay at 7.5 until, of course, I run out of stuff inside the beaker. So basically, the more you put in there, the better it is. That is called the buffering capacity. It can, react with a lot. So just to summarize a bit, you can make buffers now at any pH. All you have to do is add an acid and a base. They have to be conjugate pairs, and the acid has to be weak. That's it. If you make them equal, the pH of your buffer will be equal to the pKa.